Okay, so in this video we're looking at something called experimental probability, which is also known as relative frequency. Okay, and apologies if I sound a little bit tired, a bit mumbly. I've just woken up from a bit of a nap. Okay, so shouldn't matter. Hopefully the video is still useful, but yeah, let's just get into it. So right, experimental probability is kind of in the name, right? It's all to do with probability and experiments, right? So let's imagine we are rolling a normal six-sided dice. Okay, well if the dice is fair, or we could say if it's not biased, then the theoretical probability, so in theory, what you would expect of rolling a 2 is going to be 1/6, which hopefully makes sense, right? We know on a normal sided dice, right, we've got 6 outcomes, 1, 2, 3, 4, 5, and 6. Right, the probability of getting a 2 is going to be your number of successes, which is 1, over the total, 1, 2, 3, 4, 5, 6, hence the 1/6, which is there. However, right, how do we know that the dice is fair? Because we could just be assuming that it is fair. What could we do to test if that dice was fair? So what do you think you could do to test if that dice was fair? Well, that is where the experimental bit comes into play, right? We could do an experiment, right, and calculate the experimental probability, which is called the relative frequency, also, of rolling a 2. So literally, right, we could do some sort of experiment where you roll the dice, let's say, 100 times, and you record how many 2s you get. Okay, and the closer it is to 1/6, the more that you can be certain that the dice is fair. You can never be certain, but you know the closer it is to a 6th, the more certain that you're going to be. Okay, and then maybe you might be thinking, well, if I rolled the dice 10 times, you know, could I make a better conclusion there? Well, probably not, no, because 10 times isn't very many times. So if you roll, you know, you might actually just roll no 2s in 10 times, but then could you say that the dice is not fair? Well, you can't really be sure because it's such a small number of trials. But what about if you did 1,000 rolls, 1,000 trials, and then you can compare, right? Because if you do more trials, it's going to be more accurate. So we're kind of getting along that kind of thinking. So yeah, we could compare the experimental probability, right? So the experiment side of things with the theoretical. So what it would be in theory, which is a 6th, to see if that dice is fair, which we'll see on the next slide. Okay, and experimental probability, it's pretty much just the same thing. Well, it is really, as normal probability. It is the number of successes, so how many times, in this case, we would get a 2, over your total number of trials. Okay, so let's go and apply that now into the next slide. And again, right, experimental probability can also be referred to as relative frequency. They mean the same thing, so just making sure that we know that. Okay, so the same kind of question as before, the same thinking. We've got a dice is rolled 90 times. What is the experimental probability of rolling a 2? Okay, and again, experimental probability is pretty much just normal probability. It is your number of successes. Well, how many times do we get a 2 here? We get a 2. Frequency means number of times. So we get 2 45 times. Your total number of trials is going to be your total frequency, which if you add all of those up there, we can see, or we would get 90. So there we go, right? The experimental probability is just going to be equal to 45, right? We get 45 2s over your total number of trials, which is going to be 90. Okay, and what's that equal to? More simply, right, equal to 1 over 2 if we divide 3 by 45. Okay, so just thinking about that then, basically, right, the probability of getting a 2 here from the experiment, rolling it 90 times, is equal to 1 over 2, a half, right? In theory, would you expect to get a 2 half the times? No. Right, we said on the previous slide, the probability of getting a 2 in theory is 1 over 6. So we're going to come on to in a second that probably, right, this dice is going to be biased because the sample size or your number of trials is pretty high. To get the number 2 45 times is very high. Okay, so yeah, part B, is the dice biased? Well, two ways that we can really look at this. The first way being we can say yes, because the theoretical probability of getting a 2 is a 6th. Remember, that just means we've got 6 outcomes on the dice, 1, 2, 3, 4, 5, 6. In theory, right, you'd expect to get, you know, a 2 one time out of 6. Okay? But in the experiments, so in this thing here, the experimental probability, which is much larger, the probability is much larger at a half, right? 1/2 is much bigger than 1/6. Okay, so we can say, yeah, but bias means not fair. Okay, so if we don't know what that means, right, that word there means not fair. Okay, so yeah, I would say that the dice is biased because 1/2 is much bigger than a 6th. We can also look at this in a slightly different way. We can also say, or we could say, let's get rid of this here. we would expect to get 15 number 2s, right? Because if you roll a dice 90 times and the probability, the theoretical probability, the expected, is 1/6, right? You would expect to get a number 2 1/6 of the time. And how do you find a sixth of 90? Well, you would do 90 divided by 6. 1/6 of 90. 90 divided by 6 is 15. So you'd expect, in theory, to get 15 number 2s. But in the experiment, right, well, the probability was a half in the experiment, so you'd expect to get a 2 half the time. Well, a half of 90. 90 divided by 2 is 45. You can see, right, they are much, much different. You would expect to get 15 number 2s. We've actually got 45. So we can say with quite a lot of confidence, right, because the sample size, the number of trials is pretty high, the dice is probably going to be biased. Okay? So, right, that's something called experimental probability. There's also something we need to look at with this topic, which is called expected success, which is basically just rearranging that previous formula, but we'll look into that now. So you can also be asked how many times you would expect something to happen. So, right, there we go. The formula for this is expected success is your probability times your number of trials. That has just basically come from your previous formula, where we said that the experimental probability, or just probability is your number of successes, or expected successes, over number of trials, right? And they've just rearranged this to get this here. I'm not going to go through that, but it just comes from that, right? Just if you were wondering, it's nothing new, it's just rearranged. Okay, so let's look at a question. It says the probability of Claire scoring a penalty is 0.8. She attempts the penalty 20 times. How many times would you expect her to score? Well, using this formula here, we can just go and say, well, the probability that she scores is 0.8 and number of trials is 20. So there we go. Put it into the formula. Expected success is 0.8 times 20, the formula, which is equal to 16, which makes sense, right? The probability of her scoring is pretty high. One being she's going to score every single time, which is impossible. That can't happen. So yeah, she scores 16 of them, which makes sense because the probability of her scoring is pretty high. Okay, so what we'll do is we'll look at one kind of typical exam question here that I've got from somewhere, and then I'll give you guys 3 questions that you can give a go yourself, and then that will be the end of this video. So let's go through this one first. So John wants to test if a coin is biased. He throws the coin 30 times, and here are his results. Okay, complete the relative frequency table. Right, be a little bit careful. This is not just saying how many heads and how many tails you get. Remember, experimental probability, right, or complete the relative frequency table. Remember, right, this thing here is the same thing as relative frequency. Okay, it can be called both, right? You need to be aware of that. So it's your number of successes over the total number of trials. So these are both going to be out of 30. Both out of 30. Okay, so that's your total number of trials, which we can see is 30. How many heads do we get? We're just going to go through it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So we get 22 heads. So we get number of successes just means how many heads do you get, 22, which must mean that there's 8 tails. We'll just double check it, but 1, 2, 3, 4, 5, 6, 7, 8. Good, because they must add up to make 30. Good. That's part A done. So complete the relative frequency table. Well, that shouldn't really be, there's nothing to write in there. Right, part B, is the coin biased? Explain your answer. Yeah, well, I would say it is. Because, right, is the coin biased? I would say yes, right, because we would expect the probability of getting heads to be a half, which using out of 30 is going to be 15 out of 30. We're supposed to be getting heads to be 15 over 30. However, here it is much bigger. It is bigger at 22 over 30. Okay? Or you could say something like you would expect to get 15 heads, but we've got 22, which is bigger. Okay? Conversely, right, you could also say, just by looking at the question, right, that actually, because the number of trials, the sample size is quite small, that you could also say, actually, well, is the dice coin biased? Maybe you could say no, because we can't be sure yet, because the number of trials isn't big enough. Like 30 flips of a coin isn't actually that much, really. I mean, that could happen quite easily with 30 flips. Yeah. So you could also say no, because the number of trials isn't that big. But I would just be safe here and say yes, you expect the probability of getting heads to be half, 15 out of 30. However, it is much bigger, 22 out of 30. Or you could say something like you would expect to get 15 heads, we've got 22. It all means the same thing. Okay, so I'll highlight these bits here because that's quite important. Sorry, my handwriting is not looking good here, but it's the way it is. Right, John decides to throw the coin 150 times, calculate and estimate for the number of times it will land on heads. So it wants us to use the probability from the table here. So he throws the coin 150 times, calculate the number of times it will land on heads. Well, using the probability from the experiment, so the experimental probability of getting a heads was, so the probability of getting a heads was equal to 22 out of 30. Estimate number of times the coin will land on heads, so we want to find the expected number of successes. So how many times you expect it to happen? Well, that's going to be the probability, which is this one here, 22 out of 30, times by your number of trials, which is 150. And then put that into your calculator. So let's almost get rid of this bit here, we don't need that. Okay, I've just taken this from the table. So 22 out of 30 times that through by 150, and we get 110. So based on the experimental data, right, if you throw a coin 150 times, you'd expect to get 110 heads. And that there is our answer for that part. Okay, right. And a quick point here, note what have I put here. Something they ask in exam questions quite often is, and we've been through this, we talked about this before in a video, how could they make the experiment more accurate? Well, you could increase the number of trials. They often ask that question, right? So just do the experiment more times. Because if you think about it, like the more times, if you threw that coin 1,000 times, right, it gets more accurate. So you can be more certain that a coin is or isn't biased. Okay. So 3 questions that you can try here. You can pause the video and then go to the end to see what the answers are. And I've given you the formulas up there, which we do need to memorise, but I've just put them up here for the sake of the video. So question 1, right, on a biased dice, the probability of getting a 1 is 0.3. Dice is rolled 150 times, so probability is 0.3. Number of trials is 150. How many times would you expect to roll a 1 is 0.3? Dice rolled 150 times, so would you expect to roll, it should say a 1, I guess, shouldn't it? Would you expect to roll a 1? Sorry about that. Okay, but it's just going to be this formula here, isn't it? Because expected successes is the probability of getting a 1, which is 0.3. And we're timesing that by number of trials, which is 150. And then just put that into your calculator, and we get whatever we get. So 0.3 times 150, which is equal to 45. Okay, and that there is our first answer. Okay, so 45. Good. Question 2. A coin is thrown 50 times, it lands on tails 27 times. What is the relative frequency of getting a tail? So, right, that's just using this basic formula, isn't it? But it's just being aware, right, what does relative frequency mean? It means the same thing as experimental probability, which is just pretty much probability. It is probability, which is your number of successes, how many times you get what you're looking for, which is tails 27 times, so 27 over your number of trials, which is equal to 50. So 50, there we go. Okay, can we simplify that down? Well, 27 is divisible by 3, 9, 50. I don't think we can. I think that's it, isn't it? 27 over 50. Yeah, that's just our answer. Okay, so that is our answer. Yeah, just a 1-mark question there. Okay, using the first formula, and let's highlight that. There we go. Okay, and then last but not least, right, the spinner shown, so this spinner here is spun 300 times. Okay, how many times would you expect the arrow to stop on green if the spinner is fair? Well, the probability of getting green, if all of these spinners here are the same size, it's going to be probability of getting a green is equal to 1/5. Okay, and expected successes, we should really write that at the formula. Expected is going to be equal to, expected is your probability, in this case, of getting a green, which is 1/5, so 1/5. And we're timesing that by number of trials, which is 300. So 300, 1/5 of 300 is going to be equal to 60. So 60, that is our first answer. You would expect to get a green 60 times, which makes sense, right? If there's a 1/5 chance, 300 rolls, a 1/6 of 300 is equal to 60. Okay, good. Right, we've then got below. The table below shows the number of times that the arrow stops on each colour. Okay, the spinner is spun once more. Estimate the probability of landing on a purple. So I'm assuming, right, it means that, I'm guessing these numbers here add up to 300. Let's just double check that. Let's do 45, add 37, add 52, 94, add 72. Yeah, good. Right, these total, right, they add up to 300, which is good. Right, the spinner is spun once more. Estimate the probability of landing on purple. So it's right saying using this data here, if we spin the spinner again, so probability of getting a purple is going to be just 72. So that's right, part B up here. Probability is going to be your number of successes. So purple 72. 72 over your number of trials, which is 300. It's not, I can see why you might get confused. You might think it's 301, they spin it once more. It's just saying, right, using this data here, okay, using that data, what's the probability of getting purple? Right, it's not saying that add another one on. That is a bit confusing on that question. I'm assuming they still mean out of 300. Let's write that a little bit neater. Out of 300, and that is equal to. Look, with probability, you can leave it actually in that form. That is absolutely fine. But if you want to simplify it, it's the same thing as 6/25. Okay, on that one there. Good. Let's highlight the answer. So either of those is absolutely fine. Good. Okay, last one. If the spinner is spun 1,000 times, how many times would you expect it to land on blue? Okay, so remember, expected successes, we're expecting to land on blue is the probability of getting a blue from this table here. Right, we know that the probability of getting a blue is equal to 45 out of 300. Okay, and using our formula, expected successes, so expected is your your probability of getting a blue based on this data from the experiment, which is 45 out of 300, and we're timesing that by our number of trials, which is 1,000 now, so times that through by 1,000, and we can put that into our calculator. So 45 over 300 times 1,000, which is equal to 150. So that's part A, sorry, let's make that a bit more clear. That was part B, and then part C is down here. Let's highlight our answer there. Good, 150. Okay, hopefully that was useful on relative frequency. 20 minutes, 18 minutes, 48, not too bad. Okay, thank you.